Here's Avi and Benita, and they both get to make a choice about how they want to receive payments. Benita chooses a payment plan where she gets paid $100 the first day, and the next day she gets paid $200, and the next day she gets paid 100 more for $300. And so if you look at her graph right here, every time you go over to the right once, which is one day, you go up $100. So the first payment was $100, and on day two, her payment went up to $200, and on day three, she was paid $300. And that is a linear growth model. And so you can see that the amount of money included in her payment grew, and it makes a straight line on the graph. Abby has chosen a payment plan where she gets 1 cent the first day, double that for 2 cents the second day, double that for 4 cents the third day, double that for 8 cents the fourth day. And as you can see by the blue line on the graph, she has very little money as the days go by until eventually she keeps doubling and doubling and doubling, and the amount of money that she gets paid in each payment skyrockets to the point where it passes up Benita's payment. So you can see by looking at the table, after 18 days, Benita's payment was larger than Avi's payment. But on the 19th day, Avi's payment was larger than Benita's payment. Well, Benita's payment is called linear growth. Avi's payment is exponential growth. Benita's payment is an addition of $100 every day. Benita's payment doubles or is multiplied by 2 every day. I thought it would be interesting to look and see what would happen if Avi saved every payment and if Benita saved every payment. Who would have the most money in the long run? Well, Benita, if she saves every payment, in 21 days, she'll have $23,100 saved up. On the other hand, Avi will have $20,971.51 saved up. But on the 22nd day, when Benita has $25,300, Avi will have $41,943.03. So the total amount of payments received, if they save all of their payments, Avi will have way more money. And if you look at the 24th day, Avi will have $1,677,772.20, and poor Benita will only have $30,000. So you can see how quickly, by looking at the orange line, that Avi's exponential growth model grows.
Our goal for this video is to help you identify what the graph of different exponential growth and decay functions look like. So first of all, we need to see, what does the parent function of a growth function look like? You can always identify exponential growth because it will be a function in this form, f of x equals b to the x power, and it is a growth function if b is greater than 1. So b could be a whole number that's greater than 1, or b could be an improper fraction that's greater than 1. You can identify a decay model by looking for f of x equals b to the x, where b is between 0 and 1, which means that b is a proper fraction. So on this example, y equals 6 to the x, we are looking at an exponential growth model because we have a b value of 6, and 6 is greater than 1. We are going to graph this exponential growth function by making a table. So this is a little different than other tables that you've made because we are going to be substituting the x values in for the exponent, which is different than other problems you may have done. To find the first y value on the graph, we substitute in -2 for x. So we substitute in -2 for the exponent. And 6 to the -2 power, when you put that into your calculator, is 0.03. And that's rounded off to the nearest hundredth. To find the next y value on our graph, we need to do 6 to the -1 power. And when you do that on your calculator, it comes out to 0.17, rounded off to the nearest hundredth. The next one should be an easy one. Anything to the 0 power is 1. So the next y value on our graph is 1. The next one, 6 to the first power, when we substitute a 1 in for our exponent, that is 6. And finally, 6 to the second power is 36. So there's our table. Now we need to make the graph. Well, already you might have noticed one thing that makes graphing exponential functions very difficult. You can have very, very, very small numbers and very, very, very large numbers. So it's hard to set up your x and y axis so that you can accurately graph an exponential function. So at -2 on our graph, we have a dot at 0.03. Well, on graph paper, that almost looks like the dot is exactly at 0. At -1, we need to go up 0.17, so that's slightly above the x-axis. At 0, we need to go up 1. At 1, we need to go up to 6. And at 2, we need to go up to 36, but there's our problem. Our graph only goes up to 24, and we need it to go up to 36. So we have kind of two numbers on our graph that are so small, it's hard to graph them. We have one number that doesn't even fit on our graph, which goes all the way up to 24. So graphing exponential functions can be a challenge because they grow, or sometimes they decay, so quickly. Because of the difficulty of accurately graphing an exponential function due to the very small and very large numbers, when you're working on your assignment tonight, this is a way that you can find out the answer without graphing all of the small and large numbers, which can make it difficult to have an accurate graph. So to begin with, we look at our function, which is y equals 1/6 to the x. And 1/6 is a proper fraction. So this is a decay function. So when you're doing your homework, you would put right here that this is decay. And what that means is as the x-axis goes up and up and up, the y-axis is going to get smaller and smaller and smaller. Or in terms of a real-life problem, a lot of times as time passes, the amount of money you have or the population decreases. So when we look at the first possibility, as time passes, as we move along the x-axis in that direction, in this case, the values are increasing on the graph. So that is an exponential growth graph. So that is not going to be the answer. The same thing is here. As we move to the right on the x-axis, the values on the blue line are going up and up and up. So that is an exponential growth graph. So that is not going to be the right answer on this question. So now we have two possible choices for y equals 1/6 to the x power. And on both choices, you can see as we move to the right along the x-axis, the values displayed on the graph are decreasing as we move to the right. So these are both exponential decay graphs. In order to determine if the correct answer is the top graph or the bottom graph, we need to make a table. But we're not going to make the whole table. We're only going to make the part of the table that is useful for us picking between these two graphs. So the value that we're going to look at on this problem is we're going to look at the place where x is -1. The reason I chose that is because here's what I noticed about our graph. When x equals -1 here, our y value is 6. So this point on the graph is -1 comma 6. When I look at the other choice, at -1, the value on the graph is 4. So this point on the graph is -1, comma 4. So if we just use -1 from our table and we substitute it in for x, if the value that goes along with -1 turns out to be 6, we'll pick the top graph as the right answer. And if the value when we substitute in -1 comes out to 4, we'll choose the bottom graph as the correct answer. So now we're going to have 1/6 to the -1 power, and 1/6 to the -1 power is 6. So right here, we know that -1 comma 6 is a point on our graph. So the correct answer would be the top graph right here. That is the graph of y equals 1/6 to the x. On this example, we have the exponential function y equals 4/3 to the x power. 4/3 is an improper fraction, which has a value that's greater than 1. So anytime the b value in y equals b to the x, the parent function, is greater than 1, it's going to be an exponential growth model. So here on your homework, you're going to want to type in that it is growth, or choose growth. So knowing that it's an exponential growth model, that means as time goes by on the x-axis, or as the numbers increase on the x-axis, our line should have values that are growing. Well, if we look at this first example here, as we go to the right on the x-axis, our values are actually getting smaller. So we don't want to pick this answer. And here, as we go to the right on the x-axis, the values displayed on the graph are also getting smaller. So this is not the answer. Those are both decay models. We're looking for exponential growth. So now we're picking between the bottom left and the bottom right. And to make that choice, we're going to need to make a table. Now the problem with making a table and graphing many exponential functions is that they have numbers that are very, very small and numbers that are very, very big. So it's hard to make a graph on your graph paper with an x and y axis where you can graph an exponential function accurately. So because this is a multiple choice problem, we're going to not fill out the entire table, just the table that is most useful to us, or the part of the table that's most useful to us. And so when I look at both problems, here's what I can see. I see that at the value 2, this graph has a y of 6. So when my x value is 2, my y value is 6. On this graph, when my x value is 2, my y value is, I don't know, not quite 2. So something around 2, but not quite that big. So if I take just this place on the table, if I just figure out what happens when my x value is 2, if my x value comes out to 6 when I do the calculation, I'll pick the graph on the left. If the x value comes out to something a little less than 2, I'll pick the graph on the right. Now I could make the whole entire table, but I'm saving a little time by just checking this one point. So I have 4/3 to the second power, and when I put that into my calculator, it comes out to 1.78, rounded off to the nearest hundredth. So 1.78 is a little less than 2. It's not anywhere close to 6. So the equation y equals 4/3 to the x power is described by this graph right here.